This is the intro video for AP Calculus BC, section 4.4. We're going to be looking at the fundamental theorem of calculus, both parts. In this video, we'll be jumping to a later section in your notes here once we do this first part. Okay, so the fundamental theorem of calculus, part 1, is this right here. The integral from a to b of lowercase f is equal to capital F of b minus capital F of a. So, of course, we've talked about this before, but the equal sign, very powerful symbol, saying that the thing on the left and the thing on the right, no matter how different or same they might look, they have the same value. Pretty important thing. So let's talk about what's going on here. First of all, capital F is not a typo here, lowercase f, again, not a typo. Capital F stands for the antiderivative of lowercase f. Try to make that a lowercase if I can. So for that reason, I'm kind of jumping the gun here a little bit, but for that reason, I kind of prefer a slightly different version of this fundamental theorem of calculus, and I'll show it here to you right now. I would illustrate this by saying integral from a to b of f prime of x dx equals, let's think about what this would equal. The antiderivative, which is what the tall skinny s stands for, of f prime would just be f, right? The antiderivative would undo the derivative. And so I would write the right side like this, lowercase f of b minus lowercase f of a. It's really expressing the same relationship, but to me the nuances of lowercase f and capital F sometimes get a little bit lost, but I think with a prime there and then not there, I think it's a little more obvious to see what's, at least sort of what's going on here. So in other words, if you're going to try to evaluate a definite integral, and again I want to emphasize that a definite integral is characterized by having these limits of integration, the a and the b. To do this, you find the antiderivative first, and then evaluate the antiderivative at the upper limit, and the antiderivative at the lower limit, and then subtract. Find the difference in that order. Okay, so we're going to do one example here. We'll do a bunch more when we get to class. Here's how you could do this. So, tall skinny s, remember we talked about this in a previous class. Tall skinny s is an action word. It's an action symbol. It's telling us to find the antiderivative. So that's what we're going to do. The antiderivative of x squared minus 3 would be 1/3 x cubed, I'm just using the power rule, minus 3x. And here's how we note this. We're going to put this in parentheses and we're going to say not tall necessarily, but vertical line 1 and 2. So what that means is 1/3 x cubed minus 3x evaluated from 1 to 2. So to evaluate from 1 to 2, we're going to plug in the 2, so it'd be 1/3 times 2 cubed minus 3 times 2, that's evaluating at 2, and then we're going to plug in the 1. So it'd be 1/3 times 1 cubed minus 3 times 1. And once we've evaluated at the upper and lower, we will subtract in that order. So to finish this one out, let's go ahead and do a little bit of arithmetic here. I'll just kind of swing up this way. So that would be 8/3 minus 6, and I handle that first expression, minus 1/3 minus 3. Okay, so let's see, if we do 8/3 minus 1/3, we get 7/3. Negative 6 plus 3 would be minus 3. So let's see here, 7/3 minus 3, that'd be 7/3 minus 9/3. I'm coming up with negative 2/3. Okay, so like I said, we'll practice this a lot in the upcoming class. For now, we're going to skip ahead to our next part of our video here in 4.4. All right, in this part of the video, you'll want to skip ahead a few pages in your notes. This is Fundamental Theorem Part 2, and we kind of hinted at this already. Okay, so Fundamental Theorem Part 2 could be illustrated right here. So it says d dx of the integral from a to x of f of t dt. So a stands for a constant and x is a variable. And there's no typos here. The t's need to be there because this variable x and this variable t really do stand for two different things. The t could be other stuff, probably not a y. It just needs to be something other than x for this to work. We can talk about that a little bit more, why that is in class if you want, but just know that technically they need to be different at this point. So let me give you kind of the short answer as to what the answer is, and then we can kind of prove it a little bit as well. So as you might have guessed, the derivative and the integral, they undo each other. And so you're going to see this for an answer. It's just going to simply equal lowercase f of x. And that would be it. That's the fundamental theorem of calculus part 2. But let's dive a little bit deeper and let's figure out why that actually is. So we're going to go order of operations here. We're going to do the antiderivative first. So the antiderivative of lowercase f, we could write that as capital F. So I'm going to write this as d dx of capital F of t evaluated from a to x. So if I keep going with this, I get d dx, and I'm going to do FTC1 now. I'm going to plug in the x and the a and subtract. So it'd be capital F of x minus capital F of a. And now, finally, since we've completed the antiderivative, the definite integral, everything's complete with that, we can now differentiate. So d dx, again, that's an action saying do the derivative of f of x, capital F of x. So the derivative of capital F of x would be lowercase f of x. And here's where kind of the beauty of this comes into play. The derivative of f of a, well, f is some function. We don't know what it is, but we do know that a is a constant. And so if a is a constant, f of a would be a constant. Oops, and the derivative of it would be 0. So we're simply left with f of x for our final answer there, as I mentioned earlier. There's a little bit of an extension to this, and that would be this scenario here where u is something that's a little bit more complicated than an x. I don't know, could be a trig function, e to the x, I mean it could be all kinds of stuff, but it's something other than just simply an x, but u is a function in terms of x. So I'm going to say u is a function in terms of x. Okay, so with that in mind, we're going to try to do a similar process here, and we'll note that there's one little thing that comes into play here that's a little bit different than what we just saw. So here we go. A lot of this should feel pretty familiar. We would say the antiderivative of lowercase f would be capital F. It's evaluated from a to u. Again, u is some function in terms of x. And then, just like before, we'd say d dx of f of u minus f of a. And again, like before, f of a is a constant. So here's where things get a little bit different. Let's remember that u is some function in terms of x. It might be quite a bit more complicated than an x. Here's how this would go. d dx of f of a, that's just derivative of a constant, so that's going to be 0. So let's focus in on what's going to happen right here. So d dx of capital F is lowercase f of u. But then if you remember, whenever you do the derivative of a composite, which this f of u would be a composite, you've got to use the chain rule and multiply by the derivative of the inside. So it would be lowercase f of u times u prime. We want to remember that. So we'll do an example like this here in a second, but I just want to let you know that you definitely want to use this little trick that I showed you earlier. I'm going to erase all this up here. I'll erase the other stuff too. You see all that stuff proved there. But I would want you, and you definitely want to be to a place where you recognize you're dealing with the fundamental theorem, and you want to be able to look at this expression right here, recognize that it's FTC2, and simply go to the answer right here, f of x. The reasoning behind that is with most, if not all of the questions you might see regarding this, it is not going to be easily done or might even be impossible to find a closed form antiderivative. And so you probably won't be able to go through all those steps I just showed you. You know, down here, again, you'd want to recognize that you've got FTC2 and simply use the FTC2 trick and say, well, the answer would be f of u times u prime. That's where we want to go with this. I hope that you'll be able to get there with us. Okay, so let's do our example here. And I'll just show you what I would hope, what I'd want you for you to be able to do using the FTC2 concept. We'd look at this and we'd see that we're doing the derivative of an integral. And so hopefully we'd recognize that right away and we'd say, hey, this looks like this could be FTC2. And it is. The function that's going to be plugged in there is 2x cubed. Get everything squared away, and here's what we would do. We would recognize that the d dx and the integral are going to cancel each other out. This 2x cubed just gets dropped in for the t. So e to the 2x cubed quantity squared. Notice the t simply got replaced by the u, and we would multiply by the derivative of what we dropped in. So we dropped in 2x cubed. The derivative of that would be 6x squared, and we'd be done. So I would want you to be able to do that as opposed to trying to figure out what the antiderivative of e to the t squared is. It's a lot more difficult than you might think, and it would be much easier simply to recognize and use the FTC2 trick. Okay, hopefully that's helpful. We'll practice these when I see you next time in class.